This video is about second-order intermodulation in shortwave receivers, particularly SDRs, software-defined radios. What you see here is a low-pass filter. It is capacitors and iron-free inductors. It should have very low intermodulation, but that remains to see. I'm going to send two signals on 7 MHz into receivers and look for overtones and mixing on 14 MHz. This low-pass filter should filter out those intermodulation products that are produced within the signal generators and possibly the power combiner, which contains some ferrites. And you can see the attenuation is 105 decibels. Now, that's not really the filter properties, that's the properties of the network analyzer. Here is the setup. Two signal generators on 7 MHz, separated by 10 kHz. They are connected to amplifiers to boost the signal level. These give 6 dB gain. The signals are combined in a hybrid and then run through the filter. And after the filter is an attenuator, and it's now set to 0 on both knobs. And then the signal is routed to a 7-port resistive power divider. It's this one. And there is 6 decibels of attenuation on all the port, except the one that comes from the signal source, of course. This attenuation is either here or in front of the different receivers. So there are 6 receivers, but one of them at this moment is the spectrum analyzer. And here is what I can see on the spectrum analyzer. The signal level is 0 dBm. Peak search marker 0 dBm. There is a third signal generator on 14 MHz. It is connected through this box, which is an iron-free directional coupler, about 20 decibels, and it sends the signal also into the 7-port resistive power splitter combiner. I have switched off the two signals on 7 MHz and adjusted the third generator to produce 80 dBm, minus 80 dBm on 14 MHz. And that requires minus 44 dBm on the generator. It means there is 36 decibels of attenuation, 20 of them here, and 16 dB in the 7-port splitter, and the 6 dB attenuator that's in front of everything. The receivers are this one, the PCIe 9842. It's a digitizer on the PCI bus sampling at 200 MHz. And I'm taking the average of the samples 4x4 because I don't need a very high frequency for this, as I save some computing. This one is the Perseus, and this is the SDR-IP. And note that the S meter shows 80, minus 80 dBm on all of them, because I have calibrated for that, of course. Here is the Excalibur G31 DDC, I think it's called. This is the WSE converter chain. And here is the ELAD FDM S1. I can switch off the signal. And then we can see where the noise floor is. Minus 100 for the PCIe. The Perseus, minus 110. The SDR-IP, minus 112. The Excalibur, minus 104. The WSE converter, minus 121. And the ELAD FDM S1 is minus 108. The bandwidth is 4 kilohertz. So you can see that the sensitivity differs from 100 down to 120. That's by 20 decibels. But normal sensitivity is what you find on the Perseus. It's suitable for short wave. I have removed the notch filter and set the level to minus 50 dBm. I can turn it up, 10, 20, down and down and down. So this is quite regular, and it tells me that the overtones, this one and that one, are at the same level as the third generator, so they are at minus 80. Now I have attenuated by 50, so actually they are at minus 30 without the attenuator. That's the distortion of my amplifiers probably. Now I inserted the filter again, and it is still 50 decibels of attenuation. And we can see some phenomena, particularly in the ELAD FDM S1. There are a lot of false signals up here, so I attenuate more on 7 MHz. That is more attenuation, and again. And again. I have to go all the way down to, what does it say? Minus 80 dBm to not see anything of the overtones. It means there is no front end filter, and we have digital feedback from the data lines. This isn't as bad as it looks, because if there are many more stations on the band, this will cause dithering and spread these things out. I can go up in signal level here, and the thing corresponding to the sum frequency, the second order, is here. I continue up, and more and more and more and more and more. Here we got into saturation. So it's useful all the way up till, what do we have? Minus 10 dBm. But there is probably a risk of some false signals. But they don't grow like they would do in an analog radio without selectivity at the front. The behavior of the PCIe 9842 is to some extent similar. This is 0 dBm, minus 10, minus 20, 30, minus 40, minus 50, minus 60, minus 70. I have to go all the way to -70 to not see this intermodulation or digital feedback. And here is the Excalibur. I go up. Here it comes. This is -30 dBm, -20, -10, and here it is strong. 0, we have saturation. Now the most saturated radius, that's actually the Excalibur. It sends intermodulation into the other radius, and I think the ELAD, which looks like this, is also perhaps doing that. So I will disconnect those two. 3 radius have a regular second order behavior, or almost. That's the Perseus, the SDR-IP, and the WSE. I'm now stepping in steps of 1 dB, looking at the S-meter graphs. Now the second order is -100 dBm on all 3. And now it's 95 or 96 or something. And about -90 dBm here. It looks a little bit scary to have the same result on 3 different radios. Maybe this is a limitation of the setup. I have to investigate that. I now replaced the power splitter, the 7-port thing, and the 6 dB attenuator by a second attenuator down here. And I had before 15 dB, and now I have again the same level on the -80 dB signal here. The sum frequency is now at -100 dBm, and to get that I have to send -3 dBm into the SDR-IP. This is -3 dBm into the Perseus, and I increased the level a bit, and it grows very slowly because there are several different phenomena at the same time, but now it's 0 dBm and it is not quite at -100, the sum frequency. This is the WSE converter. It's now -100 dBm for the sum frequency, and the signal level is -11 dBm. So if you note how much lower the noise floor is, adding a 10 dB attenuator in front of it would bring it to a similar level as the SDR-IP or the Perseus. Maybe it was intermodulation from the WSE that affected the previous measurement on those two. Anyway, second order intermodulation isn't so important, because if you need better than what you can get from these radios, an external filter to suppress something that is on half the frequency would not be very difficult. Finally, I have now added 6 dB of attenuation in front of the filter, and then reduced the attenuation here by 6 dB to have the same level of the 14 megahertz into the radios, and I've checked that the result does not change. So the problem is not distortion in things that come after the filter or the filter itself. I think that's a pretty safe conclusion.